Welcome to the course on digital system design. In this lecture, we will look at registers. Registers are of two kinds. One is the parallel load register, another is the shift register. We will look at, to begin with, the parallel load registers, and then we will get into the shift registers, and then we will look at some of the utilities of the shift register, and then we will look at a universal shift register which combines the features of the shift register as well as the parallel load registers. Well, we saw that flip-flops can be used to store a 1 bit. So if you want to store certain binary information, that is the information encoded in binary form, either it can be a code that represents the character, or it can be a binary number. We need memory, and flip-flops can be made use of to realize memory devices. So to begin with, the basic unit of storage, of course, is a flip-flop, which is a 1-bit device. Now more often we need binary sequences that represents numbers, numerals or characters, which need more bits. So which means we have to have many flip-flops together to store the various bits in a binary number or in a binary code. So those are what we call as the registers. Registers are nothing but group of flip-flops. Together they store bits which are related to each other, in the sense that all these bits together represent a quantity, a number or a character code. So to review it, a flip-flop stores 1 bit of information. A register is used to store a number, n bits of information. So we make use of n flip-flops and then connect it together to form what is called as a register. And here is an example of parallel load register. It is called parallel load because all the flip-flops in a register can be loaded at the same time in a synchronous manner using a clock. So you can read out all the bits from the registers, or you can store all the bits in a register at the same time in a synchronous manner parallelly. That is why we call it as the parallel load register. Consider a case where we need a 4-bit register which is capable of storing 4 bits. It is to be mentioned that in modern processors we have registers of much larger width, 32-bit, 64-bit or even 128-bit. So all those registers which you may later encounter when you deal with microprocessors are basically built using the concept that we are going to look at in this lecture. So a 4-bit register should have 4 flip-flops. We generally use a D flip-flop to store a bit because the purpose of the flip-flop is to sample the bit to be stored and store it. And for that, a D flip-flop will be more conceptually easier because we know what to be fed to the D input of the D flip-flop. The bit to be stored is what you have to feed. And if you want to read the bit, you have to just take it from the Q output of the flip-flop. So there is a direct correspondence between what gets stored and what comes out when you use a D flip-flop as against a T, or if you try to realize it using a T or JK flip-flop. So a D flip-flop is the ideal one to store bits. So here we have 4 D flip-flops. The common clock is being used to control all of them. So here is a clock. It comes from a clock generator. It goes to the clock input of all these 4 flip-flops. These are positive edge triggered flip-flop. Then the D input of all these flip-flops are taken out and they are available, and the Q, the output of these flip-flops are made available for reading the bits of this register. We could have numbered these flip-flops are A, B, C, D, but because they are going to represent a binary number, it is better we use a common label for all these symbols and differentiate it using an index or a subscript or a superscript. Here we use Q as the common label for all the bits in this register, and the subscript I indicates which bit it corresponds to. Normally in the digital system, when we use an index to designate or identify different bits in a bit sequence, it's usually start by indexing from 0 onwards and not 1. So this bit we call it as Q0, then we have Q1, Q2, Q3. So there are 4 bits which are indexed from 0 to 3. Again, how we interpret the various bits is up to us, and that has nothing to do with the register implementation. In case if these 4 bits corresponds to an unsigned binary number, then here Q0 may correspond to the least significant bit, while Q3 may store the most significant bit. And that is why we call this flip-flops output as Q0 and so on. It is also perfectly okay to store the MSB here and LSB here, or how you interpret these bits is up to us after reading it out or while storing. But we simply, for our the requirement of differentiating one bit from the other, we use this convention of indexing it from 0 to 3 as mentioned here. So here, if you want to load into this flip-flop, what you have to do is the bits, the 4 bits which has to be stored. In case if you have a binary number, unsigned binary number, the least significant bit has to be given to this D input, and the most significant bit has to be given to this flip-flop here. And then when a clock pulse positive edge comes, the corresponding bits will be stored in the D flip-flops. Anytime if you want, you can read those bits from the Q0, Q1, Q2, Q3 outputs. So the outputs are available all the time. You don't need to wait for the clock to occur to read the output. It is always available, but the inputs are stored only during a clock transitions. This parallel register can also be laid out in a different format as you might require. So here again there is a register with 4 bits, and we use the notation A0, A1, A2, A3 to differentiate the various bits, and this is the arrangement we have made use of. You can see that there is a common clock that goes to the clock input of all the flip-flops. There is also a clear bar, to be precise, signal which can be used to clear all the D flip-flops to begin with. So if you want to store 0000 in the 4-bit register, you can do so by sending a low pulse on the clear bar. The 4 inputs to this 4-bit register denoted as I0, I1, I2, I3 are available here. Like in the same previous example, if you give the corresponding inputs on a clock transitions, these 4 bits gets changed. So, well, here suppose if you want to use this registry in larger circuitry, then whenever a clock pulse comes, the input lines I0, I1, I2, I3 are being sampled, and whatever bit that are present here will be stored in this register. Well, you may have a requirement to store the data into this register only at certain point of time. Typically when the previous stage which is connected to this register has computed some result, and that result is what you want to store. So you don't want the storage to happen in every clock period, only at certain clock periods. In this case, what do? You might tell that, well, whenever I want to store, I will give a clock pulse. Other times I don't give the clock pulse. Well, that is the right way. That is by giving clock pulse only at those times when you want to store the bits I0 to I3 into the bits designated by A0 to A3, then the transfer will take place. Otherwise, it will not take place. But in a large circuitry, the clock generator generates a clock and then gives it to various units in the circuitry through lines. So you cannot control the clock generator and suppress the clock pulse at certain time and allow the clock pulse to be generated at some other time, because those clock pulses have to be generated all the time, because some other units will be using it for some purpose of computation. So how do we selectively give clock pulse? You might wonder that then you can give the clock pulse or suppress it by using an AND gate and an enable signal. So if I put an AND gate before feeding the clock pulses to all these flip-flops and use an enable signal as the other input of the AND gate, then it will solve the problem, because when the enable signal is 1, then the clock pulses are given to the clock inputs of the D flip-flop. When the enable signal is 0, the clock is disabled and clock will not reach the flip-flops and it will not do the storage. Well, now while this is a solution which can be used under certain circumstances on simple circuits, it has certain severe problem. The problem is that you are introducing a gate in the line which gives the clock pulses to these flip-flops, while no such gate may be there in the clock pulses that feed to other part of the circuitry where different flip-flops are there. As a result of the propagation delay of this gate, the clock transitions that come to these flip-flops are delayed by the propagation delay of the gate as compared to the clock pulses that go to flip-flops in other rest of this circuitry. Because of that, a problem called as the clock skew problem comes. That is, the clock transition occur at different time. This can become a severe problem, 1 in a large circuitry, or 2 when you operate such circuitry at a high frequency. Because if the clock transition occurs at different time and different flip-flops in a large circuitry, certain flip-flops would change its values in response to the clock transition prior to other flip-flops. It might so happen that those flip-flops which change quickly might produce some results which may in turn go to other flip-flops and it might affect it. So this may result in a condition that we may not be able to predict exactly how the circuit behaves. For these reasons, we want the operation to be synchronous. Synchronous in the sense that all the flip-flops in a given logic circuitry should change at the same time, synchronously. That is why the entire class of these circuits are called as the synchronous sequential circuits. These are two different terms. Sequential because it remembers history and responds based on the input sequence. Now we put one more adjective called as the synchronous. We want all those changes to occur synchronously, synchronous to a clock pulse, and this will avoid the race problem. So when you put a gate along the clock pulse, we say that we are working with the clock in the sense that we are introducing the logic along the clock path, which has to be avoided as much as possible. If the circuitry is small, or if the frequency of operation is less, the race condition will not be severe. Otherwise, it will be severe. So, to avoid this problem, we can modify this register with parallel load as follows. So, here is the same 4-bit register, but with a little more complex circuitry that feeds the input to these register flip-flops of the registers, which takes one control line called as the load control line. Only when the load controller's line is equal to 1, these 4 parallel inputs I0 to I3 will be loaded into the corresponding flip-flops or 1-bit registers of this 4-bit register. If the load is equal to 0, then these external bits are not being taken inside and used for storage. So we can control when we want to store the inputs and when we don't want to store. And to make that happen, we manipulate the bit actually that reaches the D input of these flip-flops, and we don't manipulate the clock. You can see here that the same clock goes to all the clock input of the D flip-flops, and we don't add any external enabling circuitry in the clock path. Well, so how basically the circuit works is, when the load is equal to 1, these 4 lines I0, I1, I2, I3 are enabled in the sense that they reach the input of the flip-flops that designates A0, A1, A2, A3. That is these D inputs. That happens when load is equal to 1. On the other hand, when load is equal to 0, we essentially suppress I0 to I3 from propagating to the D input of these flip-flops, and further, but what will get stored is a question that needs to be answered. We want the flip-flop to retain the bit. So what we do is, we basically sample the output from these flip-flops and then recirculate it and store it back into these flip-flops. It might look little funny to sample the output and then store it back rather than leaving it. But this is what you have to do, because we allow clock pulse to come all the time. So whenever there is a clock transition, the D input is sampled and it gets stored. When we don't want a new input to get stored, new bit to get stored, the only way we can achieve it is to recirculate, to sample the same bit that is gets stored and then recirculate it and store it back. So this avoids the clock skew problem. Well, how does this circuit work? Let's see. Look, when the load is equal to 1, there is a 1 here. Because there are 2 NOT gates here, there would be a 0 at this point and a 1 at this point. Well, when there is a 0 at this point, this 0 that goes to the one of the AND gates that are present. See, there are at the input of every flip-flop, there are 2 AND gates which are being OR together before feeding the D input. We will call this AND gate as the top AND gate and this as the bottom AND gate. If you look at this is being replicated for every bit. So there are 4 top AND gates which are 1, 2, 3 and 4, and there are 4 bottom AND gates 1, 2, 3 and 4. So when load is equal to 1, this bit is 0, there is a 0 to the input of the top AND gates, you can see at these points. So essentially what we do is, these gates suppress this signal to go through to the D input. Whereas a 1 here means there will also be a 1 here. So these points will have 1 and that will enable the bottom AND gates. And bottom AND gate, this AND gate basically enables I's I0, I1, I2, I3 to propagate and be present in the D input. Note that only one of these AND gate will be enabled at any given time, will be opened any given time, because we tap it with a NOT gate between these two signals. So only one of them will be 1, other will be zeros. So when the load is equal to 1, we let I0, I1, I2, I3 to be available at the D input of these 4 bits, 4 flip-flops, and when a clock transition comes, they will get stored. On the other hand, when load is equal to 0, then there will be a 1 here and a 0 here. When there is a 0 here, then these gates which are connected to the I's, I0, I1, I2, I3, these gates, the bottom AND gates, basically disable I0, I1, I2, I3 to propagate, while the top AND gates will have a 1 because there is a load is 0 and this bit is 1. So the top AND gates, they allow the recirculated bit sampled from the output of the D flip-flops to come back and then get stored again. So this is a register with parallel load, properly designed. Then we will talk about what are called as the shift registers. We saw that in the case of the parallel load registers, there will be external lines, 1 per flip-flop. If we have an 64-bit registers, then 64 external lines have to come, and when a clock pulse comes, all those lines are sampled and those bits are stored. Similarly, there are as many output lines are there which has taken out. For example, here there are 4 input lines I0, I1, I2, I3 and 4 output lines A0, A1, A2, A3. Well, if we have a register, 64-bit register implemented in IC, then just to feed, apart from the VCC, ground and clock and any other control signals like load, we need 64 input lines and 64 output lines. The number of lines that go inside the circuitry, the IC chip fixes its cost. So if you want to reduce the number of lines that go to the register and come out of the register, then we can go in for an implementation called as the shift register. Here we take only 1 bit at a time and then store it at an appropriate place, and then take the other bit and store it. Similarly, when you're reading it, you will read only 1 bit at a time. So if you have 4 bits, in order to store those 4 bits of a 4-bit binary number, you store 1 bit at a time. Using 4 clock periods, you will store those 4 bits in successive clocks. Then similarly, if you want to read it out, you have to read 1 bit at a time. So you need 4 clock periods to read all these 4 bits. So it is a time consuming operation, but the number of signals that go in and come out becomes less. So a shift register can achieve it. Here again we have got a 4-bit register, but this is a shift register. A common clock goes to all these D flip-flops, and you have a serial input called as SI for short, through which bits can be sent into this register. There is a common output called as the serial output, SO for short, through which bits can be read out. So what essentially we do is, these D flip-flops are cascaded in the sense that if you call this flip-flop as the first flip-flop, the output of the first flip-flop feeds to the input of the second flip-flop. The output of the second flip-flop feeds to the third, and so on. So if you have this kind of a circuitry where bits of which are being sent will first get stored in this first D flip-flop, and during the second transition it goes to the next D flip-flop, and so on, 1 bit at a time. Well, so let's look at this operation of how bits go within a shift register as follows. So here this is the serial in, we will call it as in. It is connected to the D input. The output of this flip-flop called a Q is connected to the D input of the second flip-flop and so on. We call these intermediate points as A, B, C. So let's look at how the bits go at various clock periods. We will designate this clock period as T0, T1, T2, T3 and so on. So assume there is a 0 in the in signal at the time T0, while the value present in A, B, C are unknown. So when a clock transition comes, we go from the time period T0 to T1. So T0 is one clock period. At the end of T0, a positive edge comes and a change occurs, and the next clock period is called as T1. So T0 and T1 are the successive clock periods separated by a clock transition when the flip-flop changes. So we will see that after the clock transition at the end of T0, this in bit, whatever that is present in the in, will get stored in the first D flip-flop and it will be available at the A. So this 0 that is present in will get stored in A. But still B and C are not known to us. Well, at this time, that is in the second clock period, if you assume that this a 1 is being given to the in bit serial input, then when a transition occurs between T1 and T2, this bit 1 will be sampled and stored in the first D flip-flop and it will become available at the A during the T2. While the bit that was originally present in the first flip-flop, which was available in A, which was 0, will get stored in the second flip-flop when a transition occurs between T1 and T2, and at the clock period T2, that 0 which was in A becomes available at B, and then at one more clock period it will be available at C. So you would see that bit 0 which was originally present at T0 moves forward from one flip-flop to another flip-flop in every clock period. The 0 which was here at T0 goes to A and then B and then C, like that. And then if there were a 1 here, this 1 at T1 goes to A at T2 and then to B at T3 and then to C at T4. This one is a different bit. You could have fixed it at 0 also. Okay, these two are different bits. So again this bit will also propagate in this manner. Then at T3 if there is a 0, 0 will propagate. So this is how the shift register moves. We can view the same operation of the shift register with looking at only one bit as follows. So there is a serial input, serial output. The bits are designated as Q0, Q1, Q2, Q3. The numbering is up to you. Okay, we can call this as Q0 and this as Q3, or it's up to us. So here we have the clock. This is a positive edge triggered flip-flop, so we are concentrating on the positive edge or the raising edge. These are the points at which the transition will occur. We will call this as T0, this as T1, this whole period, duration as T1, whole duration as T2 and so on. Suppose SI, the serial input, has got the bit 1, which is indicated like this during the first clock period T0. Then when a clock transition comes, this bit 1 will just go to Q3. And in the next clock period, it will move on to and become available in the second flip-flop and be available as Q2 and then to Q3, Q1 and then to Q0 and so on. So now we will again look at this functionality of the shift register in a little bit more detailed manner, and then look at some of the utilities of this shift registers. Suppose you have got two shift register A and B. You want to transfer the contents of the shift register A to the shift register B. How do we do it? So here is a simple circuitry that can be used. You have a shift register A, it can be a 4 or 8-bit shift register. Here we will assume it's a 4-bit shift register. And another shift register B, and we use a common clock to both these shift register. The internal circuitry of the shift register is not shown. It is same as what we have already seen, but now the entire 4-bit shift register is shown as a block. This whole circuitry is now shown as a block diagram. You see that we already looked at that each D flip-flop can be a master slave flip-flop with 2 latches, and each latch would be a cross-coupled NOR or NAND gate. So we are encapsulating the circuitry and coming up with the building block at various levels. The cross-coupled NAND gates are being encapsulated into a black box called D latch, and 2 such D latch are used in a master slave configuration, and we came up with a black box or a circuitry or a building block called as the D flip-flop, H triggered D flip-flop, and these are those units. Now 4 such units connected in this manner will constitute a 4-bit shift register. Now again we will encapsulate it into a circuitry and use that building block as a 4-bit shift register, and that is what is being shown here. So in digital circuitry, this kind of an hierarchical encapsulation of circuitry will be quite often be used. So we want these 4 bits to be shifted to this B shift register, while at the same time the content of the A register should not be altered. Well, if you have 4 bits that are present in this A shift register, if the output of the A register is recirculated back and given to the serial input, then after 1 bit shift, then if you call this bit as the least significant bit and this bit as the most significant bit, after 1 bit transition, LSB will come and occupy the MSB position, MSB will be 1 lesser significant, and so on. So we are recirculating, that is, we are taking the bit from the right hand side and then putting it in the left hand side. If you do this operation 4 times in a 4-bit shift register, you can easily understand that the content of the register will not get changed, because this LSB will come to this MSB position during the first bit transfer, then it will move 1 bit towards the right, 1 more bit, and so on. After 4 such shifting, it will come back to its original position. So we have to, this can be used to restore the content of A. While the output of this A flip-flop, A shift register, if it is, that is the serial output, if it is connected to the serial input of the B shift register, and if you do 4-bit shifting, then all these 4 bits will be transferred to this B shift register. The least significant bit will eventually come to this place. To begin with, it will occupy the most significant position, and then it will come get shifted 1 bit at a time, and eventually it will occupy here. Okay. But for that to happen, we have to generate only 4 clock periods, and for that we use this simple circuitry wherein the clock is being enabled or disabled using a shift control. We already mentioned that this is not a good way of designing or working with a clock, or introducing a logic in the clock circuitry is not desirable, but it is okay if the circuit is simple and race condition will not occur. So in this simple circuitry, if there is no other circuitry that is present in this system, this design is acceptable as long as the race condition is being it's not pronounced. So we use the simple approach. So what will happen is you are looking at the clock, and here the shift control is given for a duration of 4 clock periods. On ANDing this clock with this control, we see that the only 4 clock pulses are being given to this A and B shift register. And this table shows how the bits get transferred. So the initial value of the shift register A, let us say it is 1011, and let us say the shift register B has a content 0010. After this shifting operation, we want the content of B to vanish, because what goes out of the serial out of the B register, we are ignoring it. At the end of this transfer, B register should have 1011, that is what it is present here, and the content of the A register should be retained, that is 1011 should also be present at the end of the transfer in A. Let's see how this happens. You can see after 1 bit shifting, this 1 of A goes to the MSB position. I will call this as the MSB and this as LSB, although this is arbitrary, this need not refer, these are all just bits. Okay, it there is nothing to do with the significance of bit, which only comes into the picture when we treat it as a binary number. So this bit, the LSB position of the shift A register, comes and occupies the MSB position of shift register B, while this 0 comes and occupies here, this 0 comes here, this 1 comes here, this 0 goes away, vanishes in thin air. Similarly, in shift register 1, this 1 gets recirculated and comes to this position, while this 1 comes and occupies this position, while 0 comes here, 1 comes here, and so on. After one more transition, so you would see that all these bits get transferred to the right 1 bit at a time. Now during that one, because SO of A is connected to SI of B, this shift register together acts as a 1 8-bit shift register. These two 4-bit shift register now acts as an 8-bit shift register during the transfer. So this 1 comes and occupies here, and so on. So after 4 transitions, all these 1011 will also be present here. Now let's look at a utility, an example giving the utility of the shift registers. We have, let's say we want to build a circuitry which can be used to do the addition process. So if you want to add 2 4-bit numbers, then we have seen how a 4-bit adder can be constructed using 4 full adders. Suppose you have only 1 full adder, you want to do 4-bit additions using 1 full adder only, we can do so using a shift register. Indeed, even if you want to perform a 128-bit addition process, a single full adder is enough, because you are going to essentially add only 1 bit at a time. You don't need 128 full adders to accomplish it. Although that implementation would be faster, we can achieve it in a slower pace using just 1 full adder. So here we have 2 registers, A and B, of arbitrary length, maybe 4-bit or 8-bit or 64-bit, doesn't matter. We want to add these 2 register contents and store the result back into this A register. So we can treat this A register as an accumulator. It does A plus B back to A. Okay. while the content of B register can go away. We are not bothered about it. And here you have got a full adder. One of the input to the full adder, call it as X, comes from the shift register A, serial output SO of the shift register A. The other bit Y comes from the serial output of register B. You know that when we add bits from LSB onwards, you have to take care of the carry that is generated in a bit position I when we add it along with the bit I plus 1. So to store the carry, we use this D flip-flop. So the carry that is generated at any given bit addition is being stored here and it is reused during the addition of the next bit. And the sum bit that is being produced by this full adder is being circulated back and it is stored back in this A register. There is a common clock that goes to the A register, A shift register, B shift register, as well as to this D flip-flop. Again, we control this clock pulse using a shift control. And like the previous case, although this is not a very encouraged method, it's a very simple circuitry to illustrate the purpose of how a serial bit addition can be performed. When the shift control is given, then clock goes, otherwise they don't go to this place. And each shift register has a shift control bit also in this case. So only when the shift control bit is 1, this clock will have a role, otherwise it will not have a role. Whereas for this, we separately use the shift control and the clock and AND it together before feeding the clock to this D flip-flop. So before addition, we store the data contents of the A and B shift register in the respective register. We clear this carry input D flip-flop, because to begin with there is no carry that is being present. You can later on see that we can make use of it to even perform a 2's complement subtraction, where this can be set as 1 and we include an exclusive OR operation to generate a 1's complement of B, which is added with A along with the initial 1, which will perform a 2's complement arithmetic. I can probably come back to it little later. So now what happens here is, you give the shift control for a duration which is equal to n times the clock period, where we want to perform an n bit addition. Then after each clock during clock transition, the LSB of A and B are being taken, it is added with the clock and the sum and carry are being produced. Sum goes back to the A register, carry is getting stored here and it is used in the next bit addition. First thing is, you will see that the first LSB of the sum which is produced here will get stored in the MSB of this one. At the same time, we shifted 1 bit, so the least significant bit of A, which was already made use of, is no more required, so we take it back. We take it away. So as soon as we use 1 bit in A, we have a 1 bit position available which is made use of for storing the 1 bit of the result, that is sum. As more and more bits get used, more and more bit positions will be available for us to store this result, and finally the sum will get stored. Well, if we add 2 n bit numbers, you will get an n bit result plus a possible carry out. That last carry will be present in this one. The result will be an n plus 1 bit. The n plus 1th bit, that is the carry out, will be present in this present. Now this can be used in an unsigned carry addition. You know, if you want to do a 2's complement addition, okay, if you want to convert this B into a 2's complement number and add it with this one, you can easily change the circuit to do that. A 2's complement number is nothing but a 1's complement number with an addition of 1. at the LSB position. So if you initially set this flip-flop as 1, you are adding a 1 to this summation process. And you have to generate a 2 ones complement number, which is nothing but complementing each of this bit. So if you put an exclusive OR gate in this path and tie that bit as a 1, then each bit that comes out of the B will be complemented before feeding to Y. Essentially, we will be doing an addition of X with 1's complement of Y with an 1 at the LSB, which is a 2's complement of B is being added with A. So this is one way in which shift register can be used to save the hardware. That is, with one full adder we can add. Next, if you want to even get away with this full adder, we can make use of a JK flip-flop and then carry out this whole addition. Let me just sorry.